So, in the last lecture we solved the problem of forced vibration of a simple viscously damped system. We continue with the discussion on the topic which involves vibration of viscously damped systems when subjected to harmonic excitation. So, what we did, we wrote the equation of motion . We also noticed the point that once the steady state starts, once the transient is over and damped out, the oscillation of this mass will be also a simple harmonic function of time with the same frequency, but not necessarily at the same phase. So, we note that the solution in the steady state will be of this form. Next, what we did, we substituted this in this equation of motion and found out the values of x and phi. That means, the amplitude of the resulting vibration x will be f0 and the phase difference, the tan of that then we notice that the static deflection when the same force is applied statically, that is F0 as a constant force, then the deflection of the system will be also a static deflection whose amount will be F0 by k. But when the same force is applied dynamically, the maximum displacement or deformation of the system will be x, and this quantity we have already defined in the undamped situation as the magnification factor, and which will be then we plotted the response of the system either x or the magnification factor. So, at we start at r, that is frequency r is equal to nothing but the frequency ratio when omega starts at 0 and gradually increased. So, here we have seen that this line represents the magnification factor 1 and this line represents frequency ratio 1, and the for various values of damping coefficient, as damping increases, and this particular line is for 0 damping. When we plot the phase difference phi, as you can see, the phase difference also starts at r is equal to 0, it is equal to 0, that means phi is 0. So, irrespective of the value of zeta, phi will increase, become equal to 90 degree at r is equal to 1, and asymptotically approach the value phi, because when r is equal to 0, this is 0, phi is 0. As r gradually increases, then it also increases, but when r becomes 1, it becomes infinity, that means phi becomes pi by 2, and after that this becomes a negative quantity, and obviously we will go to the second quadrant, and as r tends to infinity, this tends to minus infinity, and obviously this will tend to pi. So, this was the kind of results we received. We have noticed one thing here, that the peak value of the response or the magnification factor is not at r is equal to 1, as it was the case in case of undamped situation. So, let us find out where this peak will take place. That means, if we define this as the RP, that means the frequency response where the magnification factor reaches a maximum value, we can easily find it out by trying to find out the maximum value of so del m del r will be equal to 0 at r is equal to RP. We know it's very simple when m becomes maximum. So, how much is this? Or it will be this is del m del r at r is equal to RP is equal to or we can say the numerator must be equal to 0. The numerator is equal to 0 means or 1 minus r square is equal to square. I must here put r is equal to r p. So, the peak value of the or the value of the frequency response where the magnification factor reaches maximum is given by this. When zeta is equal to 0, that is the undamped case, obviously r p is equal to 1. There is one particular interesting situation which we will be utilizing at a later time, and so therefore, it is not out of place to discuss it here. When r p is equal to 0, that means the peak itself is at the beginning, then it only reduces, that means it is tangential here. What is the corresponding value of zeta? So, this will lead to 2 zeta square is equal to 1, or zeta is equal to 1 by . So, with this damping factor, the peak is here itself. Significance of this or use of this we will find at a later time. Here also you will find that for zeta is equal to 0.707, you will find that it will be almost a straight line for a large part of its range. Then we find another very interesting thing, that when the frequency ratio is pretty high, then the deformation of the system in the dynamic situation is far less compared to what the deformation would have been had the same load been applied in a static manner. That means, if I apply some load here, statically whatever deformation in the spring will take place, if I apply the same load with a frequency which is much higher than the natural frequency of the system, the deformation of the system will be much less. That is, suppose if there is a beam, cantilever beam, subjected to carrying some kind of a mass here, then if a load is applied here statically, the stress which will be generated or strain which will be developed will be much less compared to the static situation if the same load is applied at a much higher much higher frequency. So this is a very important observation, and we will see that this can be used in design of systems very effectively, where the system can be made much lighter compared to what it would have been if the load is static. But nevertheless, we should keep in mind that the natural frequency of the system has to be designed in such a manner that R becomes much higher than 1. There is another way of solving this problem which I will take up. The reason being that it can be not only remembered much easily, but can be effectively utilized in more complex situations, which I will demonstrate. A vector quantity harmonic quantity perhaps we have discussed this quickly in the past, but we will remind ourselves about it. So, if a vector is called x, which is x say cosine omega t, we can represent it by a rotating vector like this, which is rotating at a speed omega, and so therefore its projection, as you have mentioned before, where t is equal to 0, this will be omega t, and this will be x cosine omega t, if this is x. Fine. Now, what will be x dot, or velocity, instantaneous velocity? It will be, if we differentiate this with respect to time, we will get minus omega x, which I can write again as omega x cosine omega t plus pi by 2 is nothing but minus sine omega t. So now it is again a harmonic function of time, whose magnitude is omega x, and it is leading the x vector, or the vector representing the position, by 90 degrees. So x dot will be represented by a vector whose length is omega x, and that is leading the position vector, or position the vector representing position, by 90 degrees. If we want to now represent acceleration, then we differentiate it once more. Minus cosine omega t we write as cosine omega t plus pi. So this is again a harmonic function of time, and can be represented by a vector whose magnitude is omega square x, and that is leading the position vector by 180 degrees, as can be seen from this is cosine omega t, this is leading cosine omega t by 90 degrees, this is leading cosine omega t by 180 degrees. Fine, with this, so you can also keep on doing it. Say the third derivative will be so. Third derivative will be represented by this rotating vector. So when these four vectors rotate like a rigid body with an angular speed omega, their projections on that line t is equal to 0 will be harmonic quantities of time, harmonic functions of time. This will produce something which will represent the position, then this will represent the velocity, this will represent the acceleration, and this will represent the jar. So therefore these vectors do not have any physical existence. All the time we have to keep in mind that always only the projections along this line is what we have in reality. Okay. Now if we consider the free body diagram of the block, what are the forces at any instant of time when it is displaced from its equilibrium position by x, moving in this direction at a speed of velocity x dot and with an acceleration x2 dot. The forces are the external force. So, now these forces are harmonic functions of time. So, we can represent them by rotating vectors. So, first is the spring force. Spring force will be like if x is there in this direction, then spring force is acting in the other direction. So, what we can do, we can represent the spring force first and let the spring force rotating vectors length be k into x. So, therefore, its component along the line along which you will take the projection, it need not be always this one, it can be something else, but whatever it is, it will be kx into cosine omega t, which is nothing but this. We have to now add Cx dot. Now, x dot is represented by the vector this. So, Cx dot will be representing or will be represented by a vector which is leading this So, these two x vector, c omega x vector together when you join, they represent the total force acting on this side. Now, actually if you look into this equation, actually what we are doing, we are representing this equation by a rotating vector diagram. So, kx, we have added Cx dot, now we have to add mx2 dot. x2 dot is represented by a vector like this. So, mx2 dot will be represented by a vector which is now leading the x vector by 180 degrees. And these three together will be equal to f0 cosine omega t. So, this 3 must be equal to f0, and the whole thing as a like a rigid body is rotating with a speed omega, and its projection, if t is equal to 0 is here, then this is equal to omega t, and obviously this must be equal to then phi, because x vector is represented by x cosine omega t minus phi. That means position vector is lagging behind the force vector by an angle phi. So, this must be phi. Now, once this diagram is ready, we can derive the results directly from this. So, for example, we can consider this right angle triangle, where this side is how much? It is kx minus m omega square x this is this side. If we square it, and this is equal to this itself, we square it and add, what we get is nothing but f0 square. Now, taking x common, taking it out, so directly now we find x is equal to Now, if we divide both the numerator and the denominator by k, we get now here if we divide this by k, when it goes inside this it becomes k square, again when it goes inside this it becomes k. So, divide this by k means 1 minus m omega square by k, which is nothing but omega square by omega n square, that is r square. Now, c omega by k we have shown number of times is equal to 2 zeta r. So, we get the response, magnitude of response as we solved the equation of motion and got it. Here we got it directly from this diagram. Now, the phase difference also directly comes from this diagram. It is obviously nothing, tan phi is nothing but c omega x by kx minus and this is nothing. If you cancel x from numerator and denominator and divide both the numerator and denominator by k, c omega by k is nothing but 2 zeta r and k by k is 1 and m omega square by k is nothing but r square. So, both the results which we had to struggle a little bit and solve the equation, we directly get from this diagram. So, this approach is very convenient. It also gives a physical insight all the time. So, for example, here we find that at r is equal to 1, the phase difference is always pi by 2. That means, irrespective of the damping, the phase difference between the excitation and the response is always 90 degrees. Now, why it is so? It can be very easily explained with the help of this diagram. Say when r is equal to 1, r is equal to 1 means what? R is equal to 1 means it means m omega square by k square root is 1 or m omega square is equal to k or obviously omega square is equal to omega n. But anyhow, that is not important, that you know that it is the resonance, but k is equal to m omega square. If k is equal to m omega square, then how much will be this length? This will be 0. That means m omega square will be, that means this will come here, the situation will be something like this. When kx is equal to m omega square x, because k is equal to m omega square, it is very obvious that this will be a rectangle and this will be 90 degrees. Now, it is irrespective of this damping C, it could be something like this. Suppose damping, we make a different damping. So, it will go here, but again the diagram is going to be again a rectangle and this 90 degree will be always there. So, we find that at k is equal to m omega square, the spring force is exactly cancelling the inertia force, or spring force takes care of the inertia force. So, the externally applied force always takes care of the damping force, and therefore, the phase difference between the response and the excitation is always 90 degree irrespective of the amount of damping is present. So, this gets very clearly explain with the help of this diagram. It gives much better physical insight. Another advantage of using this diagram is that more complex situations can be solved with ease without going into a very solution of very complicated differential equations. We will take up one example for our own practice and also to demonstrate that statement which I have just made. So, sometimes what may happen, the dashpot or the damper may not be connected to the body and the fixed foundation on its two sides, and maybe one side is mounted or one side is connected to a point which has an elastic connection with the foundation. So, this class of problem is interesting So, our problem is this, that we have a system where now we find one end of this dashpot is connected to the body, but the other end is connected to a spring whose other end is connected to the foundation. So, this now there are two springs because the dashpot is mounted elastically, and obviously therefore two spring constants. So, we call the spring coefficient for this one as K1 and the coefficient of stiffness for the other spring as K2, and C and M are there. Now, here we will find that first let us try to see what will be the equation of motion. Now, to do the to write down the equation of motion, when it has gone to a displaced position x. Now, what will be the damping force? Now, damping force is, or the force exerted by this dashpot will be C into the relative velocity between the piston and the cylinder. Now, velocity of the cylinder is same as x dot, but the velocity of piston is not 0. In the previous cases, the velocity of the piston was 0 and the relative velocity between the piston and the cylinder body was same as x dot, and so it was a C x dot. But now, this end of the piston is also deforming, and let us now call this as y. So, this will be C into x dot minus y dot. And of course, the free body diagram of this dashpot this end he is applying C into x dot minus y dot, and the other end has to be then the same. But now if we consider the spring K2, this is obviously stretched. It must have stretched if it is deformed by y here. So, the force here will be nothing but now this is equal to this is very clear, and these are all massless, we should keep in mind. So, one thing we find from this, that Cx dot minus y dot, which is the force acting here, and K2y is the force here. So, they must be same. So, Cx dot minus y dot must be equal to K2 into y all the time. Now, the equation of motion for this we know is m x2 dot plus C x dot minus y dot plus K1 x equal to, and the other equation you have got now we get two variables and two equations. As a typical procedure for solving this equation is that we have to eliminate one. As you can see, eliminating y will be easier. What we can do, that first let us substitute this is equal to this here, or mx2 dot plus K2y plus Q1x equal to f0 cosine omega t. We are solving it in great details because this type of coupled equations, this is a technique which may be useful in other situations. Or now we differentiate both sides of the equation with time once more. So, it becomes now mx3 dot So, you see now what happens, we can express y dot as a function of x and its derivative. So, if we now substitute this here, we will get this. So, it will be mx 2 dot plus Cx dot minus Cy dot. So, we have to multiply by minus 1 and C. So, it becomes plus this also will be plus this will be also plus So, now we get when equation completely in terms of x and its derivatives, but you can see it is a higher degree equation. It involves x3 dot, x2 dot, x dot, x, so on. So, we can write like this. So, solving this equation is going to be again problematic. Problematic in the sense you have to assume x is equal to again some x into cosine omega t minus phi and substitute it here and then solve the equations. Much simpler way could be perhaps if we again try to use the rotating vector approach. So, we know that x can be represented by a vector like this, and we multiply it by k1. So, k1 x is this term. X dot will be leading it by 90 degrees and we have to multiply that by 3 into this. Now, k1 by k2 we can represent by a quantity, maybe ratio lambda, but at a later time. Next, there is another term which will be now still leading the whole thing by and this is the left hand side. So, this is the right hand side. Now, right hand side has now two terms now. One we find is f0 cosine omega t so it is f0. Another one is again sine omega minus sine omega t. Minus sine omega t can be written as plus c omega f0 by k k2, and minus sine omega t is nothing but cosine omega t plus pi by 2. So, therefore, it will be again leading this vector cosine omega t vector. So, this will be c omega f0 this is 90 degrees, and obviously the angle by which the displacement lags the or response lags the force is phi. But our first interest will be to find out x. So, we now use geometry and trigonometry. So, this one we get f0 square plus c omega f0 by k2 square must be equal to this square plus this square. How much is this square? And how much is this? This much is this square root, and so when you square it, we get this. So therefore, now x square is equal to, if you take f0 square out, no, sorry, it is a reasonably complicated term, but still nevertheless we have found out x without solving any equation from this diagram, and we can also tell what will be your tan phi. Tan phi is going to be this divided by this. That also can be found out. So without going into the further details, I will give you the answer. So magnification factor, that is x by f0 by k1. In this case, if we apply some load statically, its deflection will be guided only by k1 spring. We can easily see that, because whatever this in the steady state or zero velocity situation, this will not transmit any force. So the only resistance to deformation will be k1. So f0 by k1 is the static deflection, and that is given by so magnification factor is somewhat complicated. Now there are two springs and their stiffness ratios are represented by lambda. The natural frequency of the system is considered to be undamped case, square root of A1 by m, and static deflection obviously also is controlled by the first stiffness, which is the K1. Now here, this one, if we plot, now when let us consider zeta is equal to 0. We will have some interesting zeta is equal to 0 means zeta of course is c omega by q1. When zeta is equal to 0, then obviously there is no contact or no connection. So it becomes a simple spring mass system, and its natural frequency is obviously square root of k1 by m, and the response will be, as we have seen before, it will start from 1 and drop to 0 asymptotically. Another extreme case, so this is zeta is equal to 0. Another extreme case will be when C is infinite. If it is infinite, it means it is rigidly connected. So this becomes simply then equivalent to a system. Zeta is equal to 0 means and zeta is equal to infinity means this is the case. And obviously the natural frequency and that ratio will be then 1 plus this. So for this, it will again behave like a simple undamped case, and the frequency response or the magnification factor diagram will look be like this. Static deflection is now one thing is very clear, that this particular frequency ratio, the magnification factor is not depending on the damping factor. It can be easily found out that what will be the value of this. How do you find it out? That the magnification factor when zeta is 0 is given by 1 by when zeta is 0, magnification factor is this, but since it is beyond this, we have to take the minus sign. And this must be equal to the magnification factor is same for the other case when zeta is infinite. When zeta is infinite, we can ignore this, so it becomes 2 lambda zeta r. Similarly, you can ignore this and it becomes 2 zeta square below this, and so finally what we get is, if we call this as r star, we get lambda by this is for zeta equal to infinity and zeta equal to 0, and they are same at this value.
Or it
So,
has to be something like this.
R star, you can easily
all
solve
the
this,
different
and
values
if
of
you
the
zeta, the curve has to always pass through that. So, best value of that will be where this is the maximum value. With magnification
zeta,
factor
for which
at this value of R star
becomes
we can
the
then
peak
show
value
very
RT
easily will be independent.
that
of
is a
this.
case where you will
So,
find
all the
that
curves, the deflection of the system
of different
in the
values
whole
of
range
zeta
will have to pass
the
through
frequency, forcing frequency may vary.
That means it will be something
this.
like whole range, the peak value of the deformation or displacement will be kept to a minimum. So, this is another strategy which is a good example of design, that if you want to design something for which the frequency of excitation is continuously varying over a wide range, then we can always design it in a manner so that its maximum deflection will be minimum in the whole range if we design it in this fashion. I think this was a good demonstration to indicate the advantage of using the rotating vector diagram. I have not meant this, but this should be always indicated. So, we will proceed with our discussion for cases where the damping is not exactly of viscous nature. What can be done in such situation? Simple analysis